Good morning. My name is Bill Howard. I'm the Product Line Manager at Makino, and I'd like to welcome you today to our seminar. We're going to talk about competing globally in the mold market and looking good, which is a combination of a case study, a technical case study, and an evaluation of the economic impact. I'd like to start out by giving you a little bit of an overview of what we're going to talk about today relative to competing globally in the mold market. First off, what are today's mold shop challenges? I think you all know what they are. We're going to try and summarize those for you. The second thing, we're going to challenge you to action. We're going to ask you to change the paradigm. Rather than viewing manufacturing as a necessary evil to produce molds, we would like you to start viewing manufacturing as a weapon. Not only a weapon, but a competitive weapon that you can defeat your competition with. I'd like to talk a little bit about what we see or what we think the elements for success are. And those include not only the machine tool, the application, the tooling, the techniques, and carry on through the execution of a case study that we're going to present. We decided we picked a case study here. What we wanted to do was we wanted to show new techniques and new technology, but rather than be esoteric or out in the abstract, we wanted to bring it home with a real life, real example, and a real product to demonstrate those techniques in hard metal so that you can really see. It's one thing to talk about something. It's something completely different to go out and do it. And I think you'll see in Made in the Shade, it's an application for sunglasses, and you think, well, gee, what's sunglasses? But it's an optical application which has very high definition geometry, high finish surfaces, and it's also a consumer product which demands good feel, good finish, and a good look. Well, you can say, okay, we've talked about a case study and the techniques and the technology. What's it mean to me? What's the potential impact upon my mold shop? We're going to present us based upon the case study, the Made in the Shade case study, and the examples, the techniques that we used, and the actual results that we've achieved. We're going to convert that into the impact, literally, financially, upon your mold shop and the competitive situation that you find yourself in today's mold shop. Today's mold maker challenges. What are the challenges of today? Well, obviously price, delivery, and that price and delivery has driven an intense competition. That intense competition has led into offshoring as a means to try and get a cheaper price or a quicker delivery. In addition, there's been other factors such as escalating raw materials. The cost of the raw materials as it goes up squeezes the margins. There's also a shrinking skilled labor pool. There are fewer and fewer people that have the skills, the craftsmanship that goes into mold making. At the same time, there have been technology advances such as CAD/CAM systems, high-speed machining, and hard milling that put an even greater demand upon the labor pool. The marketplace itself has seen significant user, supplier chain, and base shifts. There's been a dramatic shakeup in the automotive industry. There's been the entry of new players. And as those players come in, they have their established chain and supply base. Therefore, you have overcapacity, which results in some consolidations and realignments within the supply chain and the shift in the base. And then finally, there's the business challenges. Do I scale up for efficiencies, or should I become a niche player and become very specialized and very focused upon a small segment of the market? There's also the challenge in business. Do I grow and invest and modernize to compete versus downsizing and liquidating the assets? Once again, we need to think about that paradigm. And isn't it time to go on the offensive and to look at mold building totally differently, in a new light? Why not use manufacturing as your competitive weapon? How would the competition view you if you changed the paradigm and your business looked like this? What if you cut your lead time in half or more? In the case study we talk about today, we're actually going to see where we've taken some core and cavity manufacturing reduced by 40% and some lens manufacturing down by almost 86-87%. What if you could significantly reduce your manufacturing times, your cycle times? You could notably reduce your inventories. If you could double or triple your turns, reduce your investment in work in process. How much work in process do you currently have sitting on your shop floor? What if you could slash your manufacturing cost? We'll talk a little bit here in the case study later about reducing the manufacturing cost by almost 50%. We can minimize the direct and indirect labor. In some cases, we can eliminate or avoid the associated expenses such as traveling, living, expenses for expensive at the builder, at the molder modifications to the mold. And the bottom line is you'll do all of this with an improved quality product. You'll get away from hand working. There'll be no hand working or benching, no fitting, venting, or adjustment, and your first shot will produce a good part. The approach that we use to present this information is a case study. What we wanted to do is we wanted to capture a real-life application. We didn't want it to be a theoretical approach or a mathematical approach. We wanted to go out and capture a real-life case, a case that where there is an existing cavity today, so we have data on how it was traditionally made, what the challenges were. We wanted a case that would be, or an application that would be challenging. This particular case is a sunglass. Now, you might not think that sunglasses are critical, but number one, you need to understand that this particular sunglass was invented or created by an individual that is an ophthalmologist. So the geometry of the optics are critical. The other thing is it's a consumer product, and as you know from being in the mold business, there are demands on a consumer product relative to the fit and the finish and the flash and the feel and the appearance of that product. This case study is to go in and literally produce a cavity, not using the traditional method, but using a unique, different method to break the paradigm and to basically use manufacturing as our means to address the challenges being faced by today's mold shops. Things like delivery, cost, hand polishing, hand finishing, and eliminate those things and really focus in finding out what we can do and how that would impact your business. Let's go into some of the background of this particular project. We went out with a particular mission in mind. We were looking for a new product introduction. We wanted to be quick to the market. We were looking for something that was a high-quality molded product. This is a very critical design in that there's no hinge between the front of the glasses and the side of the glasses. So it's a no-hinge design, which means you cannot have flash or any type of inaccuracies in the cavity. And we're looking for superior surface finish, obviously on the optical, but also for the feel and texture of the glasses. And we were looking for someone that was willing to try a new approach, someone willing to upset the paradigm. Some of the key characteristics that we were looking for in this particular application are some of the same characteristics you find in the mold business every day. Number one, we were looking for a 3D parting surface. That 3D parting surface is critical in this particular case, in many cases, because of the appearance and the feel of the blending and parting lines. The no-hinge design also is critical because we cannot have flash. There can be no flash or trim required, which means the action in the mold, particularly the closing of the cams in the mold, has to be right there, because otherwise the hinge won't work, we'll have flash, and the appearance and feel of the parting lines will not be good. There's also challenging surface finishes, not only to maintain the optical characteristics, but to enhance the stylish look and feel, as well as the hinge design of the product. Some of the other project characteristics we were looking to reduce lead time to market. We wanted to slash the machining times. We wanted to compress the mold assembly times, getting rid of the hand working and polishing. And we also wanted to streamline the after-build activities. Furthermore, we wanted to reduce the costs by eliminating the benching or polishing. We didn't want to have any spotting, no spotting or finishing prior to mold prove-out, and we wanted the first part to be a good part. This case study, Made in the Shade, which talks about the production of a mold for sunglasses, high-performance sunglasses, has three major components: the core and cavity blocks, the lens inserts, and the cams. The key objectives and techniques that will help you change the paradigm and utilize manufacturing as a competitive weapon that we were trying to exhibit in this case study, number one, is no hand fitting. Most folks today are cutting the core and the cavity to zero stock. They're literally going in and cutting them right to the tool path, and then they're spending a lot of time hand scraping. You may be doing that out there today, hand scraping out the cavity literally between the core and the cavity of a zero stock cut. The reason this was done that way in the past was because there was a fear that if you undercut or went to a negative stock situation and you didn't have good control over the tool path or the thermal growths, then what was going to happen was you're going to overcut, and now your cavity was too big, and literally the only way to recover would be to weld back in and then rehand finish. There's no need to do that today. The tools exist. The machine tool and the tooling exist. The techniques exist. And we'll show you in this case study how we can cut to a negative stock situation and have no hand working and no flash. We machined the cavity blocks to zero, and we machined the core to a negative stock, 10 microns or 40 millionths of an inch undersized. The lens pockets were actually EDM'd, and we EDM'd those to about 3/10,000ths of an inch oversized. And we actually machined or EDM'd the pockets out prior to cutting so that there was a lot less machining because the lens pockets were removed. The lens actually itself was machined to zero stock, so the clearance was actually on the lens pocket. The parting surfaces were not relieved from the edges. The entire parting surface matches. This is different than most parting surfaces, literally where there's a relieved area. It improves this particular approach. The parting surface is not relieved from the edges, the entire parting surface matching. It improves the part surface alignment and reduces the flashing potential. It also reduces or eliminates totally the need for manual relief of the mold. Now, the traditional approach that a lot of folks are using out there would be that they would drill all the holes in the soft. You would then go in and rough machine it in a soft state. Then you go out and heat treat the cavity. We'd heat treat to probably 48 to 50 Rockwell C. Then you bring the block back in, grind it to size. You'd wire EDM the lens pockets and the cam clearance, and then you would finish machine and then send it to the bench where you're benching and polishing. The approach that we're going to take in the case study here is we're going to drill all the holes in the soft, then we're going to send it out and heat treat. And when we bring it back, we'll grind the blocks to size, we'll wire EDM the lens pocket and the cam clearances, much like before, but then we will rough and finish machine literally to the final cavity. The technique that we've used in this particular case for the core and cavity block machining is what has traditionally been called a Z-level offset climb cut type approach. We start literally at the outside of the cavity and pass around the outside of the part, constantly moving in the Z-plane, in a constant Z-plane. And then once we complete a pass, we'll then step down and step over in X and Y, and then again repeat in a constant Z-plane, stepping down each time. This allows us to maintain a constant chip load, and the climb cutting ensures that the chips are moved away from the cutting action on the part. As far as tooling, what we're looking for here is, number one, a balanced tool. It has to be balanced. The other thing we're using here, I'm sure most of you would use also, would be a collet type holder. The collet type holder, we're actually using that because of the collet itself absorbs some of the cutting vibrations. So in combination with the stiffness and rigidity of the spindle and the mass of the machine tool, it provides us with a very smooth, chatter-free cutting mode. We'll start by zooming into the V56, showing actually what we're looking at here is the cavity being machined. We're cutting in the area of where the lens inserts would slide in and out of the cavity. In this particular case, further cutting on the cavity. There's a Z-level offset type climb cutting on the internal portion of where the lens insert would fit into the mold. And one of the critical areas of this particular cavity is along the side of the sunglass, basically the wraparound portion. As I said earlier, this is a no hinge type design. This is also the cam area where the cam comes in, and as the mold closes, the cams will come up and literally shut the mold off. So it's critical here that we have, number one, excellent surface finish and exacting dimensions and tolerances so that we don't have flash once we close the mold. Basically, we're using the same approach in that we're going in with a Z-level offset type feed, we're climb cutting, and we're actually, though, here using what's referred to typically in the industry as a stock model recognition. What we're doing is we're remachining the toolpath in the critical sign frame of the sunglass area, or the cam area of the cavity, using a stock model recognition. We use smaller and smaller tools, and the stock model recognizes and identifies the area that requires further machining, having stock remaining. Techniques identical to what we used on the face, in that we start on the outside, move in a constant Z plane, and continually step down and over as we step in down in Z. This allows us to maintain a constant chip load again, and the climb cutting ensures that the chips are moved away from the cutting area. In this particular case, because of the size of the tooling and the reach, you look at some of those tools are length to diameter ratio 12:1, so they're long tools. We're using a very highly balanced tool, a G2.5 balance, and actually shrink fit, so that the shrink fit, the length to diameter is very stiff, very rigid. We have virtually very little run out. You'll notice the excellent run out characteristics of the tool. So very good stiffness and rigidity, even though we're a very long tool and a very good reach down into the cavity. What we've got here is literally a process chart, if you will, showing the traditional approach of the we talked about earlier: drilling the hole soft, rough machining soft, heat treating, grinding the block, wire EDM in the pocket, finish machining, bench and polishing. You'll notice the total time there's about 30 hours. This is the new approach, where we drilled the holes, heat treated, grind the blocks, then EDM the pocket, and then rough and finish machine. Total time's 18. In this particular timeline, what we've done is summarize the traditional approach at the top with the new approach in the bottom. As you can see, the process outlines exactly as we had talked about earlier. The traditional approach to drill all the holes in rough machine and then heat treat and so on down through bench, and where the new approach is obviously different. We heat treat, grind, lens, pocket, and cam clearance, then rough finish machine. You notice the big difference here is rough machining soft and also in benching and polishing. Key elements to notice here is the difference in the overall processing time. On a traditional approach, it took us 30 hours, whereas the new approach, it takes us 12 hours. So what we've done here is we have eliminated 12 hours worth of time and ultimately cost and lead time out of this manufacturing process. That's a 40% reduction in the time required to produce the core and cavity blocks. The cams are the second item that we need to manufacture for our mold cavity. Actually, in this particular mold, there are 6 cams, as you can see highlighted there. The two, well, they're all critical, but the 2 critical ones are the ones on the side that literally cut off or close off the cavity along the side of the sunglass, and that's also the area where the critical no-hinge connection is at. The traditional approach for the cams would be to rough machine the geometry in a soft state. Then heat treat the block. We would heat treat again to a 48 to a 50 Rockwell C. Once the blocks come back in, we would grind the blocks to size. We would wire EDM the actuator pocket, then finish machine. But you'll notice there's a lot of benching and polishing left to be done. On the new approach, actually we start by heat treating the block. We would grind it to size, wire EDM the actuator pocket, and then rough and finish machine to our final dimensions. In this particular case, we're using exactly the same type of approach that we used previously for the tool path. It's a Z-level rough offset type climb cutting approach. We would start once again on the outside of the part, moving constant to the part. We would move in a constant Z plane. We would step over and step down in a constant amount, which would maintain a constant chip load. Climb cutting also again ensures that the chips are moved away from the cutting edge. We've used balanced tool holders here. Again, the tools are smaller. They're all 4 millimeter or smaller in diameter, ball nose end mill. So obviously the balancing is critical, the 2.5 G. And also the use of the shrink fit tooling gives us outstanding stiffness and rigidity, outstanding balance. You notice the TIR of the tool is very good. The finishing cut we approach a little differently. It's what's referred to traditionally in the market as a parallel cut, climb and conventional approach. We literally move back and forth in parallel cutting lines across the surface, which means we would alternately be climb cutting and conventional cutting. The feed rate or step over and depth are coordinated to provide an extremely consistent look and motion to the cutting action. The result is the fact that we generate a 10 RMS surface finish on the cam surface. We utilize balanced tool holders, a G2.5 with a shrink fit, and an outstanding TIR on the tool. These again are very small, 4 millimeter and less in diameter tools. These are the side pockets. This actually is the wraparound area portion of the sunglass. This is critical because of this is where the cams close off the cavity, and it's also where the no hinge design is at. It's another view of the side area, which is the side of the glass. This is the cam area that's closed off by the cam, and also the area where the no hinge design is. You notice the extremely long length, the diameter ratio of the tooling. The process diagram of that traditional approach shows, just as we talked about, the rough machining, heat treating, grinding the blocks. Total time here of 11 hours. By contrast, the new approach where we heat treat first and then grind, EDM, and then rough and finish machine is 6 hours. As you can see on the cams, we have reduced the traditional approach from 11 hours, which includes benching and polishing, down to the new approach of 6 hours. So that's a savings of 5 hours on the cam manufacturing process, or a reduction of 45.5%, 46%. The final and possibly the most key element are the lens inserts. The traditional approach to producing the lens inserts would have been to drill all the holes in a soft state and then rough machine the geometry in a soft state. Then heat treat, once again to a 48 to 50 Rockwell C, EDM the profile, then finish machine the lens, and then a significant amount of benching and polishing. In the new approach, we took a rather dramatic or very different approach. Obviously, you notice we drilled all the holes soft, and then we sent it out and had it heat treated. When it came back, we rough and qualify machine. Now, I want to explain the qualify. You'll notice that what we're going to do here is nickel plate and then ultimately diamond turn. Well, in order to nickel plate, well, two things here on this rough and qualify. Number one, keep in mind that this is the lens surface, so it's critical to maintain the geometry and the integrity of that optical surface. So we want to hold that to a very tight tolerance. The other thing is, because we're going to nickel plate it, it's critical that we get a very consistent microsurface finish so that the nickel plating will adhere to the surface. So when it says rough and qualify machine, that qualify sounds a little rough, but keep in mind we're getting to very tight geometry there because of the optical surface, and we're getting down to a 20 RMS finish for the nickel plating. We then send it out, it's nickel plated. When it comes back in, we finish machine the profile and the lens. Once again, it has nickel plating on. It is critical to the consistency and the geometry, the integrity of the optical surface, that we finish machine that lens surface and qualify it prior to the diamond turning, so that there is a qualified stock level prior to the diamond turning. So it's critical that we do that. So therefore, the finish machining of the profile and the lens is done to get that down to about a 20 RMS microsurface finish, and then that is then taken to a diamond turning optic to get the final optical surfaces of the sunglass. The machining of the lens inserts is a little bit different. What we're doing here traditionally, very traditional approach, is a Z-level rough. It's a profile offset climb cutting. We actually have, and you can see there in the picture, it's a 16 millimeter 6-fluted tool. And we're profiling about 16 millimeters down the outside depth around the profile of the lens insert. The X and Y stepovers are very small compared to the rather deep Z-axis steps. So we continue to machine from the outside of the part, moving constantly into the part. We move in a constant Z-plane or depth, and we maintain a constant chip load. Climb cutting again ensures that chips are moved away from the cutting surface. We've utilized a collet type holder again here. That again helps us to absorb the cutting vibrations in combination with a stiff and rigid spindle. It maximizes the mass of the machine tool, provides smooth, chatter-free cutting. The finish cutting of the lens insert is parallel cutting, which is alternately climb and conventional across the surface of the lens. What we're looking to do here is consistently move back and forth in cutting lines across the surface, alternately climb cutting and conventional cutting. The step over and depth are coordinated to provide an extremely consistent look and motion to the cutting action, with the result being a 20 RMS surface finish on that surface. And this is qualifying it for the diamond turning. We utilize a balanced tool holder, 2.5G, with a shrink fit, provides outstanding stiffness and rigidity for relatively small tools. Comparing the traditional approach of manufacturing the lens, drilling the holes, rough machining, heat treating, profiling, DMing, finishing the lenses, and a huge amount of bench and polish time. There's 20 hours of bench and polish time there. To the new approach, you'll notice that there's 4 hours. And you notice the nickel plating and the diamond turning there. So when you look at the two side by side, we've went from a 28-hour traditional approach to a 4-hour new approach, which means we've eliminated 24 hours of processing time, or an 86% reduction in the overall manufacturing time of the lens inserts. In summary, we can take a look at the total processing time of the 3 major components: the core and cavity blocks, the cams, and the lens inserts. The traditional approach would have required 69 hours. The new approach requires 28 hours. So we're looking at almost a 60%, 59.4% reduction in the overall manufacturing time. You may look at that 60% and say, well, gee, how much am I really going to recognize those kind of changes? What you really need to do is walk around your facility and look at the numbers of cavities that you're sitting there working on by hand polishing or scraping or polishing and buffing, all that manual labor that goes into that manufacturing of those cavities. I would challenge you that there's probably a significant, maybe more than 60% overall reduction that you might be able to see. Really depends on what you're manufacturing and what you're manufacturing it with. But I would challenge you that if you're traditionally doing your cavities, I would say 60% might be a low number. Reducing the manufacturing time has a number of other benefits. One of the complaints today that we started out with was lead time or delivery. The traditional approach, and we know because we had went out and worked with a manufacturer here, the lead time for the prior sunglass mold had traditionally been 10 weeks. Our new approach, the lead time to manufacture the new sunglass mold, was 4 weeks. Yes, as you look around your shop, just consider what you could do competitively, not only globally, but with the guy down the road, down the street. If you could suddenly, overnight, reduce your lead time by 60%, a cavity that you would traditionally take 10 weeks to build, you could build in 4. I would say that that would make you very competitive with virtually any shop anywhere. We've talked a little bit about the manufacturing process. We've talked about the hand fitting, hand scraping. Well, mold startup is another very labor-intensive process. We've taken a look at here is the traditional approach, where you typically spend some time in a spotting press at the mold builder. Then you ship the mold and cavity and typically your best spot and fit guy to the sampling press at the molder, and it takes you a while to get the first good part. Our new approach was to basically not to spot, not to hand scrape, not to hand finish. We were going to go directly into the sampling press at the molder, and the first shot was the good shot. What we've got here on the top is the traditional approach, where typically, and again we have numbers from the previous generations of this type of cavity. The spotting press at the mold builder was about 20 hours, spent 4 hours in the sampling press at the molder, and so you're 24 hours before you got your first good part. By contrast, in our new approach, we've got virtually no time spotting at the mold builder. We spent a total of 2 hours in the sampling press at the molder, and that was including the install, warm up, and deassemble time, and our first part was in fact a good part. So you've taken 24 hours down to 2 hours. That's a reduction of 22 hours, or a 92% reduction. And the one thing to remember about this is typically you may be a mold shop where everybody's right down the street, but a lot of these molds are going quite a distance. So not only do you have the time that's here, but you also have the travel and living expenses to support that installation, the spotting and sampling at the molder. Now let's take a look at the entire process. We've talked about the manufacturing, we've talked about getting the mold started up. What we've done is outlined the traditional approach on the top, where you have the manufacturing lead time of 69 hours. Then you've got the sampling press time, the spotting press time. It's a total of 93 hours, whereas in the new approach, the manufacturing lead time, the 0 spotting press, the 2 hours in the sampling press, we've collapsed from 93 hours for the entire process down to 63 hours. That's a 67.7, almost a 68% reduction. That's 2/3. We have cut our entire process time to build this cavity and produce our first good part by 2/3. Once again, the question becomes, if you could overnight reduce your entire process time, not only your manufacturing time, but your spotting press and sampling press to get to the first good part, if you could reduce that by 2/3, how would your competition view you? Now, obviously, we have to come to the financials. We've also done a cost analysis, a mold cost analysis summary on the traditional approach versus the new approach. And you'll notice a lot of the costs, the mold base and the accessories and the material and the heat treating are fairly similar back and forth across. There's some big differences down there and highlighted in red when you look at the benching and the hand fitting. The bottom line here is that the traditional approach, the mold cavity, would have cost about $40,550. With our new approach, the mold cavity was $21,900, almost $22,000. So there was a savings on this particular cavity of over $18,000, almost $19,000, $18,650, or almost a 46% reduction. We've cut our cost. Not only did we collapse our lead time, but we've cut our cost virtually in half. We talked earlier about price and delivery being key factors, key challenges being faced by the mold industry today. Again, think back. We've just cut our delivery from 10 weeks to 4, and we've cut our cost by half. Where would that put you competitively in today's market? Let's summarize the sunglass mold. We've seen almost a 60% reduction in our component processing time. And the details are there, 69 hours to 28 hours, 40% on the core, 45.5 on the cams, and 86 on the lens. A 60% reduction in lead time from 10 weeks to 4 weeks. 92% reduction in mold startup time. 68% reduction in the entire process time, and almost a 46% reduction in mold costs. Saved $18,650 on this one particular mold. How many mold cavities do you have currently flowing through your shop? Some other benefits, well, we decreased the time to market. That was one of our key objectives. We reduced our time to market by 60%. We're 6 weeks quicker, from 10 weeks to 4 weeks. So we have the potential, or our folks we work with have the potential of 6 weeks worth of inventory and sales on whatever they're going to use our cavities for. We've reduced it 68% in the entire process. What's the value of that? Well, depending on the element, the product you're introducing, it could be priceless. It could be that you've now got an immeasurable competitive advantage, not only in the marketplace with your product, but with the mold cavities that you're supplying to your vendor, because they recognize you are quicker to market. We've increased our inventory turns by 250%. We went from 10 weeks to 4 weeks. Well, that's 5.2 turns a year to 13 turns a year. We've reduced our carrying costs. Now, this may not sound like much, but if you look at what it costs you to carry that cost of that project, it cost us about $330, $327.51 in savings using a 7% per year cost of money. Again, it may not seem like much on this project. It's less than 1%. But if you're doing $1 million in business, that's $8,100. For every $1 million in business you do, that's a cost avoidance for carrying cost of money. Estimated spotting press time at the molder, we saved 20 hours at the molder. Well, number one, we reduced our direct labor. We reduced our travel and living expenses. If we assume $2,000, and it could be more depending on where your customer's at, again, that's 4.935% of the project cost. It doesn't seem like much on this one little cavity, but if you're doing $1 million in business a year, 5% of $1 million is almost $50,000 that you could save simply by not having to spot at the molder, putting it in, getting the first shot, good shot. You could reduce your travel and living expenses. That first shot, good part. The mold was in the sampling press for less than 2 hours, and that included mounting it, heating it up, and tearing it down. There was no hand fitting, no venting, or adjustments. And the first shot did, in fact, produce a good part. What's the value of that quality and craftsmanship image of your mold shop to your customer? Some final benefits. If you think back about all this, if you could reduce your lead time from 10 weeks to 4 and your cost by 50%, you could beat the lead time of your competitor worldwide, not just down the street, anywhere. And you could beat the cost of your competitor. Other benefits include establishing a reputation, to be known for your work. What we're trying to show here, it's very difficult to show in photos, but you'll notice on the traditional parting line, the very stiff, rigid definition and the marking, clear marking of the parting line. And it really detracts somewhat from the quality and the image of the product that our customer is trying to produce versus the upper picture, which is the new parting line, very smooth, very clean. Matter of fact, in some cases, you can't even see where the parting line's at. It's another look. This is actually looking up from the bottom or down from the top of the glass, looking at the traditional parting line on the one side and the new parting line. You've provided unsurpassed quality and a feel and image that just can't be matched. What are the keys to changing the status quo? It requires a new way of looking at the world. The new world of business requires an instinctive appreciation of a different logic. You need to start thinking of it as the money value of time. Well, one of the first keys is using the right tools. We needed a machine tool with unparalleled 3D accuracies. It needed to have outstanding stiffness and rigidities. We needed to be thermally stable, had to have a high-speed spindle for productivity, and unequaled 3D control capability for the details that would be required in manufacturing this cavity. We also wanted to utilize the right techniques. We wanted to utilize high-speed machining and hard milling. What are the key elements that you should look for in a machine tool to provide you with the accuracy and precision required to achieve these type of manufacturing tolerances? What we have done, we have incorporated hand-scraped guideways, highly precise alignments, providing exacting surface contact with built-in lubrication pockets. They are meticulously matched to mating hardened and ground guideway surfaces, provides accuracy over the entire travel of the machine, a tight control over alignments, and it minimizes lost motion, creating an extremely accurate platform. In addition, it's exceptionally stiff and rigid for outstanding cutting capability. You're looking for a machine tool that is hand fit so that you don't need to hand fit each and every mold that you manufacture on it. Another thing that you need to look for is a spindle. The spindle needs to provide obviously high RPM, but it also needs to be stiff and rigid, and it needs to be thermally controlled. At Makino, we realized this early on, and we have patented a number of features that we incorporate into our spindles. Things such as core cooling, maintaining the temperature of the core of the spindle, under race lubrication, a technique utilized for lubricating the bearings from under the race, and jacket cooling to maintain temperature in the bearing preload area, the spindle motor area, the upper bearing area, and the spindle housing. The third element that brings it all together is the machine tool, the spindle, and obviously the control. Anybody familiar with the mold industry recognizes that you need to be able to have high definition, three-dimensional, high accuracy control over the axis slides, and also control over overshoot or undershoot as you do three-dimensional machining. What Makino has recognized over the same time frame, as you can see by the various patented features that we've incorporated into our control, is that the geometric intelligence, or GI and super GI control, were developed specifically for die mold applications to permit high speeds and high feed rates, but yet extremely tight tolerances. That's what separates those who can manufacture dies and molds and those who cannot. In addition to the control, speed and accuracy are key elements. We have enhanced the control with what we call Super GI. It's a geometric package that allows you to shorten machining time in high definition die and mold applications, yet utilize high feed rates and high spindle speeds and high accuracies in the shortest amount of time possible. As you'll notice, it can enhance the performance anywhere from 15 to 30% over the previous generation of SGI 0.3. Not only is it critical that you have the right tools, it's also critical that you utilize the right techniques. At Makino, what we've found is it is very important for us to not only provide the machine tool, but the techniques that you can utilize with that machine tool to enhance your performance in 3D mold applications. The right techniques and the means of communicating those techniques include things such as technical publications, technology transfer classes or seminars where we literally do process training relative to mold and die manufacturing, and obviously support through service users groups, manuals, and advanced training and assistance. Experience also helps one to identify the right partners. It is critical in today's world that you have the right CAD/CAM systems to create the tool path. We've worked with folks such as Delcam and CAM Tool. It's critical that you have balanced tool holders and also high performance cutters. Okay, we've completed the case study. We've gone through the technical data and presented the case and the improvements of the new process versus the traditional process. But the real question, I guess, is how does that apply to me? What does that really mean to my business? What does that mean to a typical mold shop? Well, the first thing we need to do is figure out exactly what is a typical mold shop. So we needed to go out and profile the business or the industry to try and come up with a definition of a typical mold shop. Then what we want to do is take the techniques that we've applied in the case study and apply them to what would be the traditional financials of a mold shop to show you the impact of these techniques upon your business. What we had to do was go out and kind of construct from economic indicators, and actually this data is taken from the Industrial Mold Manufacturing Economic Census done by the United States Department of Commerce. On average, over the last X number of years, 5 years in this case, there's about 2,505 or just over 2,500 mold shops. Those mold shops average about $5.3 billion in shipments or sales. Those mold shops employ about 48,000 or so, 48,324 employees, which means if you divide the numbers out, the average shop out there has about 19 folks. And again, if you divide the numbers out, that means the average mold shop annual sales is about $2.1 million per shop. Well, there are those big guys out there. Everybody has the big fish that dominate the pool. And so here's an economic profile of the top 20 mold makers. And this actually comes directly out of Plastics News. Those top 20 companies, although they represent less than 1% of the number of shops, they control almost 16.2% of the total dollar volume of molds. And they employ about 11.2% of all employees. When you look now, you really have the big 20 and the rest of the folks. The big 20, as you can see, are about $42.8, $43 million a shop in sales, about 270 employees, and about $158,000 to $159,000 per employee. And the rest of us folks are about $1.8 million with about 17 folks and about $102,000 an employee. So that's really kind of how the mold shops break down. For this economic model, we're going to use the numbers we've shown here. Now, the other thing that we've noticed is labor content over the last 5 years or so has actually been coming down. You've been doing a good job of managing the labor. However, the margin, the middle line there, remains constant. And the problem is the material costs are going up. As you can see, material costs are increasing. We're looking at here is a profile of your total cost. And total cost is about 42% is in material and about 58% is in labor. That labor further breaks down about 70-30, 70% in direct and about 30% in indirect labor. So if you break it into the three major elements, you got the biggest cost element is about 42% of all your cost is material, about 41% is direct labor, and the other 17 or 18% is indirect labor. Now, going back to margins over the 5-year period for the economic study, the average margin is about 32.3% margin. So now let's get back to this economic model based upon the sunglass mold that we've already talked about as our case study. Therefore, we can now define a typical mold shop. It's about $2.1 million per year in sales. It has about 19 employees. You're working on we've used 30% margin. Well, let's go back. We said we had a 46% reduction in mold costs. Well, obviously, if you reduce your cost and maintain your selling price, what you've done is you've increased your margins. Actually, if we assume a 30% of margin here, you've increased your margins from 30% to 62.2%. Well, that's a 207% increase in your operating margins. So if you did the same level of business, manufacturing as per the case study, $2.1 million in business, your margin would be $1.3 million versus the $630,000 million that $630,000, $0.63 million in the case example. So you have a 207% increase in profitability on the same volume. Well, or another way of looking at that is you're making more margin on every mold. So you could literally cut your selling price to compete and still be more profitable than you are today, and you could be more profitable not only with your price, but your delivery as well because you've reduced your lead times. Let's look at that 60% reduction in molding lead time. Basically, your inventory turns have increased 250%. You went from 5.2 turns a year to 13 turns a year. Well, what's happened now is you're passing work through your facility 2.5 times faster than what you currently are or currently were doing. That means you've got new capacity. You have a newfound capacity. You could literally take your $2.1 million business, expand it by 250%, and you could become a $5.25 or $5.3 million business. And you could literally grow the business from a $2.1 million to a $5 million business with the addition of no brick and mortar or people. It's simply working smarter and better with the right tools. If you could do that, if you wanted to grow the business, that $5.25 million would result in $3.3 million in profit. So basically you end up with kind of three scenarios here. You could continue on the traditional approach, $2.1 million in business with about $630,000 in profit, or you could do the same $2.1 million in business, not absorb the extra hours and time that you found by being much more efficient, and you'd actually make $1.3 million in profit, which means you make more money. Now you're able to get business you couldn't formally get or couldn't even quote. Plus, you stop losing business to the shop down the street, or you could be competitive with anybody across the globe, no matter where they're at, because you can compete not only on price, but on delivery, and your quality is unsurpassed. Or let's look at the third model, the new approach, where you absorb these newfound hours as a result of the new techniques and breaking the paradigm using manufacturing as a key competitive weapon. Now you're a $5.25 million business, and your profitability is $3.3 million. You've also gotten out of that fishbowl of being one of the small guys and are now one of the mid-size or larger players in that marketplace. In summary, let's look back, and have we talked about everything we said we were going to talk about today? I think we've clearly identified what today's mold shop challenges are. I think we've set an example of how you can change the paradigm and view manufacturing as a competitive weapon, not only to compete, but to be successful and dominate the marketplace with extremely good price, very, very good and competitive lead times, and outstanding quality. What are the elements for success? Well, it takes the right machine tool, it takes the right techniques, and it takes the right experience, background, and exposure to bring it all together. We've shown in the case study, Made in the Shade, the new techniques and the new technologies. And I think we've shown in the quick financial overview the potential impacts upon your mold shop and what that could mean to you and your business today.